Hello, everybody. This is one of my projects which I made using Verilog in EDA Playground. The name of the project is ALU 4-bit adder with integrated CPU and ROM properties. So the ROM is for the program's memory and the CPU is for the control of the entire program's different modules, which are functions. So this is a project that I did using Verilog and EDA Playground, and it's trying to simulate how a computer would take information from memory and use that to do various mathematical operations, and then use the CPU to control all that movement and store those values back into the memory. It's something that all of our computers do, and programming languages have made this process very simple. But to get more deep into the computer's architecture, you have to learn Verilog and another programming language which tackle these transistor level operations. So these are my two files. The first file here on the left is kind of a compilation of multiple files. It has the memory right at the top, this entire section. This is like the exact place where we're able to store the values. And then it has the CPU, which controls all the different modules. Here you can see that we are importing like the module, instantiating that into the CPU as well as the ROM, and then also the ALU, which is on the right. So this is our adder, which basically its essential case is to take inputs and then an ALU selector, which basically determines what operation you want to do and provides an output. And so if you look here, it's almost similar to a switch case where we are just taking the selector and like either doing various operations depending on what that selector's upcode is. So here we have all of these, and then this is where the actual code is being run. And then lastly, the test bench is just for logging purposes so that we are able to see the output of our program. So in this particular instance of the program, what I tried to simulate was basically the memory having a variable a, and it has the value 3. And then after that, I assign a new variable b, which is equal to a plus 2. So b would be equal to 5. Then I have an if statement where I check if b is greater than 4, and if it is greater than 4, then I assign a new value to b, which is 0. So that's basically this entire code's purpose, but I can change the instructions in the CPU and the memory to change those like values depending on the program's purpose later on. So let's pull this up. This is the logging surface, and let's run the program. And here you can see this is like the entire log of everything. It's basically just a chart of at different clock cycles, what are the values of the different variables. So you can see at t equals 0, all the values for either a or b and also the ALU like result is all X, which means that they don't have an actual value right now. And we see that over time that actually changes. ALU out is 3. And ALU out is always going to be one cycle, like it was one cycle ahead of the actual values here. Because, and then you can see A is equal to 3 is registered in this cycle at t equals 45. And then it's always gonna be like one cycle ahead. So we see that over time at t equals 105, we get that a equals 3 and b equals 5. And this is our like original statement here. We said that a equals 3 and then b equals a plus 2. So that's what we're getting here. And then over time, we're checking whether or not b is greater than 4. And at the end, since it is greater than 4, we are putting the b's value as 0 now. So at the end, you can see that it has successfully run the simulation, and we're able to get the actual output that we wanted. Thank you very much. You can check out this project on my GitHub, and I'll be posting this video on YouTube as well.